Hello, I'm Iman Fatma, registration number 23I6104, and I'm the team lead for this project from the National University of Computer and Emerging Sciences, FAST, Islamabad. This project was completed with the valuable contribution of my teammate Hadia Salman, registration number 23I6026. Together, we designed and implemented a simple yet functional electronic piano circuit using a 555 timer IC, which simulates piano tones through basic electronic components.
Let's break down this simple digital logic design. Piano uses a 555 timer IC to generate musical tones. At the heart of the circuit is the 555 timer IC labeled U1, configured in astable mode to act as a square wave oscillator. This oscillator produces sound frequencies that we can hear through a connected speaker labeled LS1. To start, we have a power supply BAT1 connected to power the entire circuit. C1, a 10 nanofarad capacitor, and a resistor R8 and R7 define the base frequency of the oscillation for 555 timer. The output of the timer is taken from pin 3, which is then connected directly into the speaker through capacitor C2, which blocks any DC component and allows the AC sound signal. Now moving on to the right side of the circuit. This is where the piano functionality comes into the view. We have a series of push buttons switches which each connect to the different resistor R1 through R6. These switches are in parallel and each one connected to a unique resistor in the circuit. When a button is pressed, it changes the resistance in the circuit, which is in turn modified the frequency of the signal output by 555 timer. Since frequency is inversely related to the resistance in A-stable 505 configuration, pressing each button produces a different tone, mimicking a different musical note. These notes are then heard through the speaker, effectively turning the setup into the basic electronic piano. So, in essence, 555 timer generates the tone, the resistor and the switches control the pitch, and the speaker plays the sound. It's a very simple yet elegant demonstration of how digital logic components can be used to produce an analog sound.
How it works. The heart of the circuit is the 555 timer IC, which is configured in A-stable mode. In this mode, the 555 timer generates continuous square wave signals of different frequencies. These signals are then sent to a small 8 ohm speaker, which converts them into sound. What controls this frequency? Each of the 7 tactile push buttons is connected to a different resistor. When you press a button, it changes the resistance in the circuit, which in turn changes the frequency of the output. This variation in the frequency produces different tones, just like the keys of a piano. We connect all our 1K resistors as shown in the circuit. We place the 555 timer IC on the breadboard and connect pin 4 to pin 8 to VCC and pin 1 to ground. Connect pin 2 to pin 6 to the 100 nanofarad capacitor. Connect the pin 7 to the Viper of the potentiometer. The other terminals of the potentiometer will be connected to the network of push buttons and resistors and to the VCC. Connect the output pin 3 to the 10 nanofarad capacitor and speaker. In this circuit, the 555 timer IC will work as an A-stable multi-vibrator, producing a square wave of different frequencies at the output. The speaker will produce different sounds depending on the frequency of the signal. To change the frequency of the output signal, vary the total resistance of the circuit by pressing different switches. So every time you press a button, a different amount of resistance gets connected to generate a different frequency square wave, and the speaker will produce different tones. Pin 6 and pin 2 will allow retriggering of 555 timer IC after every timing cycle. So we will connect these pins together to the ground through a capacitor. The output pin 3 is connected to the speaker through a 10 microfarad capacitor, and the fourth pin is connected to the VCC to avoid any sudden resets. The circuit worked exactly as intended. Each key successfully generated a unique tone, and the system was stable and responsive. The differences in pitch were clear, proving that the use of varied resistor values allowed accurate frequency control. This project demonstrates the basic principles of sound generation and frequency manipulation using electronic circuits. Thank you for watching and listening to our explanation of the electronic piano project. I hope this gave you a clear understanding of how simple components can come together to create something musical and interactive.